hopefully you've had an opportunity to attempt balancing this equation on your own. In this video, I'm going to walk through its solution. So we have pentane, or C5H10, undergoing a combustion reaction with oxygen to produce the products carbon dioxide and water. And our goal here is to make sure that we have the same number of each element on both sides of our arrow right here. So I am going to start with carbon or hydrogen and leave oxygen for last because it has two different products that it is a part of, and so that'll make it a little bit more complicated to solve. Our carbon and hydrogen are both only in one reactant and one product, so it's a more straightforward balancing. For carbon, I have 5 carbons on my reactant side. That's a subscript of 5 times a coefficient of 1, giving me 5 total carbon atoms. And on the product side, I just have 1 carbon atom. I have a subscript of 1 and a coefficient of 1 currently, giving me 1 carbon atom. So since I have fewer carbon atoms on the product side, I will balance by increasing the coefficient in front of carbon dioxide. If I put a 5 in front of carbon dioxide, I'll now have 1 carbon atom per carbon dioxide times 5 carbon dioxide molecules for 5 carbon atoms. And now my carbons are balanced. I can do the same thing for hydrogen. I have 10 on my reactant side and I have 2 on my product side. If I put a coefficient of 5 in front of my water, then I'll have 5 water molecules, each with 2 hydrogen atoms, giving me a total of 10 hydrogen atoms. That balances out with the 10 subscript in my reactant side after my hydrogen. So now I have 10 hydrogens on each side of my reaction arrow and 5 carbons. The only thing left to balance is oxygen. I'm going to do that by first tallying up the oxygen on each side. On my reactant side, I have 2 oxygen atoms. And on my product side, I have 5 CO2 molecules, each with 2 oxygen atoms, for a total of 10. And I have 5 water molecules, each with 1 oxygen atom, for a total of 5. And when I add these up, I have 15 oxygen atoms on my product side. Well, I have a molecule of oxygen that has 2 oxygen atoms per molecule, and I need 15 oxygen atoms. So I really need to have a coefficient here of 15 divided by 2. I like using fractions when balancing equations, but you could also write it as 7.5 as well. If I have 15 divided by 2 oxygen atoms and each, or molecules, and each molecule has 2, then I would have 15 oxygen atoms. But we need whole numbers when we have a chemical equation, because you can't really have half of an atom or molecule. So we need to do something to represent this. This divided by 2 here is a problem, or this 0.5 if you're looking at it as 7.5. So the easiest way to handle this is to just multiply all of our coefficients by 2. This is very similar to if we had a multiple ratio of 2 to 2 to 2 to 2. We could divide everything by 2 and have a ratio of 1 to 1 to 1 to 1. So we want to multiply by any number necessary to make sure that all of our numbers are actually whole numbers. In this case, the denominator is 2 in my coefficient that is a fraction. So if I multiply by 2, then I will no longer have a fraction for that coefficient. And when I multiply by 2, I'm going to be very careful to make sure that I multiply every single coefficient, even the ones that aren't written because they are in number 1, by 2. So this 2 distributes out to the reactants and to the products. So I'll have 2 pentane molecules plus 15 oxygen molecules will produce 10 carbon dioxide molecules and 10 water molecules. And now I have a balanced equation.